Katrina here, and today we're going to talk all about continuity at a point. This video goes hand in hand with my previous video about limits because it's super important to understand limits and continuity and how they work together in calculus. So first of all, we're going to give the definition of when a function is continuous at a point and all the criteria that it has to meet. We'll then look at a few examples to help us understand this on a deeper level. So first of all, by definition, our function f of x is continuous at f of a, so at some point a, if and only if these three criteria are met. Criteria number one, f of a exists and it's defined. So again, that means our function at a has to exist. Secondly, the limit as x approaches a of f of x has to exist. So recall our video on limits that in order for a limit to exist, both the right-hand side and the left-hand side have to approach the same value and both exist independently. And the third criteria for continuity at a point is that not only does the limit have to exist, but it has to equal the value of the function at x equals to a. Okay, so now that we've got the theory, let's dive into the examples. So I drew out some very pretty drawings for all of you over here, and we're going to determine whether each one of these situations if it is continuous at A or if it is discontinuous at A. So for this first example over here, we can see our A over there. And let's go through the three properties. First of all, does our function exist at A? Well, we can see right over here that we have a solid point. Yes, f of A exists. So f of A exists. Okay, let's jump to our second criteria. Does the limit exist? Well, we can see that as we approach A from the right-hand side and from the left-hand side, we're going to have different values. So that means the limit as x approaches A of f of x does not exist. So right away, we fail on the second criteria, so therefore it is not continuous. So I'll be using CTS as my abbreviation for continuous. Okay, on to example number 2. So over here, let's see. So first of all, does f of a exist and is it defined? So f of a exists over here. This is where we have our solid point. So our criteria number 1 is met. F of a exists and is defined. What about criteria number 2? Does the limit exist? So we want to see the limit as x approaches a of f of x. So first of all, let's look at the right-hand limit. So as x approaches a from the right-hand side, okay, our function, let's call this number over here 2. So our function approaches 2. Okay, so we got a value. And now let's look from the other side. So we got our right side there. Now let's do our left-hand side. So as x approaches a from the left-hand side, we can see that our function also approaches 2. So they're equal and they both exist. Therefore, the limit exists and it equals to 2. Okay, let's see if this satisfies our last criteria. So our last criteria states that the limit as x approaches a of f of x has to equal to f of a. Well, we said that f of a exists, but it exists up here. It exists at 5, and our limit equals to 2. So 2 does not equal to 5. So this is a really funny case where we're going through all the criteria. It all looks amazing. And then suddenly we can see that we have this kind of removable discontinuity right over here, where that for some reason at A our function does not exist where the limit does, but in fact it exists somewhere else. And because of that, that means that it is not continuous. So it fails this criteria, so therefore not continuous. Okay, let's move on to our third example. So right away here, we can see that f of a is defined and exists. It's a point that lives along this curve. Secondly, if we were to take the limit, so we're going to approach it from the right-hand side and the left-hand side, we can see that they will equal the same value and both exist. Therefore, second criteria is met. And third criteria, we can see that the limit as x approaches a of f of x equals to f of a. So there's no discontinuity here, no removable holes here. This is some sort of polynomial, so we also know that all polynomials are continuous and there's no abnormal behavior around this point. So therefore, it meets all three criteria, so therefore it is continuous. That's awesome. And now let's look at our final example over here. So this looks like some sort of rational function that we're dealing with. So first of all, let's go through criteria number one. Does f of a exist? So we're looking for f of a. Well, we can see that a exists on the asymptote of this function. And we know that asymptotes are lines in which our function does not exist. So that means that f of a doesn't even exist. So if f of a can't exist, it doesn't exist, then that means that there is no possibility of this function being continuous at f of a if f of a doesn't exist in the first place. So that means that this one is not continuous at a because f of a does not exist. And there you have it. You've learned multiple criteria to determine whether a function is continuous at a point or not. So be sure to write down these three criteria and then these examples that you can use as reference. So make sure when you're checking for continuity at a point to kind of go through your checklist one by one to see if it meets all the requirements. If you enjoyed this video, please drop a like and subscribe for more fun and easy to follow math videos. It's great seeing you and looking forward to seeing you next time.